I'd like to introduce the Analog Explorer, the next shield in a long line of ACES supplementary PCBs, designed by ACES for ACES. Now, what does the Analog Explorer do? Well, it provides two different types of analog outputs, specifically two different types of ADCs. Now you might be asking yourself, Shibley, we already have ADCs. We got the amazing shield designed already. Well, there's an issue with that. That only does analog display. It doesn't actually create any analog voltages. So, I created this. This has two main sections: the motor PWM signal and the R2R ladder. First, I'll discuss how the motor signal works, and then I'll discuss how the ladder works. Important notice: the motor segment is situated on the bottom half, while the ladder segment is situated on the top half. Now, how does the motor segment work? Well, by now you've probably noticed the fairly large DC barrel jack in the bottom left-hand corner. That is to supply the motor. Now you might be asking yourself, why can't we power that with the normal voltage that's supplied to the Arduino, or in this case, the DDP? Well, motors are a bit hungry, so to say. They like voltage and they like current. Those are two things that can't really blend well with microcontrollers or any digital logic. So, a separate power source is needed. But how do we interface the two? Well, a power MOSFET is used to control that. That's that big TO220 chip you see right smack dab in the middle bottom, the IRF 520 N-channel MOSFET. Now, we already know that the ATtiny can output PWM signals. However, those are a bit staticky, a bit noisy. So to filter it, a low-pass filter is included. Those are 100 nanofarads and situated just to the left of the TO220 N-channel MOSFET. Now, to the right, you'll notice a 1 mega ohm resistor. That resistor is to make sure we don't blow anything up. While the pin is being configured to output at the very start of the program, there's a chance that it might create a feedback loop within the MOSFET. So, to fix that, since MOSFETs are voltage driven, a massive resistor is included, because we don't need any current. Now, it's a diode to allow the MOSFET and motor to safely drain themselves when powered off, and that's all connected to a screw terminal, where you can screw in any DC hobby motor. Here's how the R2R ladder works on the Analog Explorer. Well, first off, let's figure out what's the output resistance of this circuit. Well, using a fancy little thing called Thevenin's theorem, we can figure that out. It's divided up into equivalent circuits that are independent and can be analyzed as such. Now, if we ground all the bits so they're all 0, we can analyze the output resistance in the most simplistic way possible. If we take a look at B0, it acts as a divider, heading both to ground. Well, that simplifies it. The resistance of that is just R. Now, let's take a look at B1. There's something similar about this. The two resistors on the left are in series, and they can be combined. Now, that's the same case as the start. It can be made R. Wait, I've seen this. This can cascade. Oh. Well. It's just R. The output resistance is just R. Therefore, that gives us the overarching definition of what the output resistance of any R to R ladder will be. R. It's that simple. So, now that we've figured out what the output resistance will be, how can we figure out what each bit will contribute on a voltage level? Well, using the same Thevenin's theorem, we can figure that out with only a few more added steps. But one difference will have to be made. We're going to need to change this over to voltages. First and foremost, all the bits have been changed to some sort of voltage. It can be treated as just a simple high. Now, if we analyze each segment, now, this time we're analyzing it as voltage, we'll notice that for the voltage at bit 0, which we're going to analyze this entire time, the first one acts as a voltage divider, a perfect one to be exact. That perfect voltage divider means that at that line, that VB0 line, it's going to be half the source voltage there. Now this can expand. This will ripple. If we remember from last time, the resistance will be R plus another R, so 2R. So it repeats. It's another half voltage divider. We can trace this all the way along, rippling down each one, thus resulting in each increment essentially having it again. So, how can this expand? This only does VB0. We don't want to do this for each one. Well, it's fairly simple. VB1 is just one less halving than VB0. And that gives us our formula. So, the output voltage is the summation of all the independent voltages. This is something known as superposition. So, VB0 will get halved a total of 4 times, and it'll be 16. And then VB1 will be 4, and then VB2 will be 8, and VB3 will be halved. And we add these all up, we'll get the whole source voltage, the voltage that will be presented outward.